So we have a pretty cool experiment to look at today. It's nice and simple, but does a surprisingly good job of measuring something that you might think you would need more complicated tools for. Before we get into that, I'll just want to talk a little bit about what sound waves are and some of the consequences of their properties. So sound is a compression wave. So what that means is if you have a bunch of air molecules, imagine these are just sort of air molecules in equilibrium. A sound wave propagating in this direction might look at one time like this. These ones bunched together, these ones kind of spread out. And then at a later time would look something like this, where you have the sort of bunch has moved along. And so it's a disturbance that's propagating in this direction. The actual air molecules themselves don't make it very far. This one might get pushed over a little. This one might be in sort of the same spot. This one could even be pulled in this way. But as the sound wave is moving, traveling to the right, it's the disturbance that's propagating, not the molecules themselves. So that's a good thing to keep in mind. We frequently will represent it as, something like this, where this might be a graph of pressure versus displacement. And so a propagating wave might look at a later time like this, and then later like this. So this would be some initial time, a little later, and then a little later. So now if you take a look at this animation, on the top we have a wave propagating to the right, and on the right there's a graph of pressure versus x. In the middle there's a wave propagating to the left, and if you look carefully you'll see that the wave propagating to the left at the right boundary has the same value as the wave propagating to the right. So what that means is the middle one that's going to the left could be interpreted as a reflection of the top one that's moving to the right off of that right edge. And on the bottom, there's a visualization of what happens when you superimpose those. So if you add the top wave to the middle wave, what you get is the bottom wave. And this is a standing wave where it's basically a superposition of a right moving wave and a left moving wave. And the phase is such that they basically add together. So for our experiment today, we're going to use this to measure indirectly the speed of sound. So the way that this works is we'll have a tube that's open at the top and it's full of water. And we're going to put some sound in. Sorry, let me get that on screen. So the sound wave is going to travel down and reflect off the water and then travel back up. And if the water is in the right spot so that the reflected wave adds to the incoming wave in the way it did in that animation, then what will happen is we'll get a standing wave in the column and the sound will get louder. So graphically, you might represent that as a wave like this, where this signifies large amplitude and small amplitude. Now this is in the sort of displacement picture. I talked about sound as a pressure wave, but you can think of it also as displacement of the air molecules. And the reflection here happens when the molecules can't displace, and so you get a wave bouncing back up. It turns out that you'll get a resonance or standing wave in the tube if the wavelength and the speed of sound is such that you can fit a half-odd integer number of waves in there. So that might look like this half wavelength. It might look like this, where you have basically 1.5 wavelengths. So that's like a full wave and a half wave. And by measuring the distance here, if we know how many waves are in there and the distance, then we can figure out the wavelength. And if we know the frequency, we can use the relationship that V for sound is equal to the wavelength times the frequency. So if we know two of these things, we can figure out the other one. We're going to figure out the wavelength by finding the standing waves. And we'll know the frequency because we'll be generating it, and that will allow us to calculate the speed of sound. Okay, so here's what I have set up to demonstrate this experiment. We have the tube here that's filled with water, that's connected via a hose at the bottom to the can right here. And so I can move the water level in the column up and down by moving the can up and down. Up at the top, there's a position sensor in blue that sends a sound wave down, reflects off the surface of the water, comes back up to the position sensor, which then, using the time that that process takes, calculates how far away the water is. So I'm using that to record the level of the water in the column. In black right here is a sound level sensor that's basically just a microphone used to measure the level of the sound. And then the earbud here is hooked up to my phone here, which has a function generator. So if I turn this on, then we get a sine wave playing out of the earbud into the tube. Okay, so I've got capstone here, and I've set up a plot of the sound intensity versus the position of the water level in the tube. So the x-axis is using the position sensor to measure the distance to the water level. So as I move the water down, that position is increasing, and we can watch the sound intensity and see what the sound level is with the function generator on. So what I'm going to do is run through this without talking, but I'll start recording and slowly move the water level down. We should see a resonance somewhere around here at about 19 centimeters. You should see the sound intensity level increase. And I'm going to also try and hold the microphone up to the tube so you can see if, we'll see if we can hear it as well. So let's give it a shot. Here we go. I'll turn the function generator on and get the tube in position. And let's see how this works. Okay, so there's a little bit of weird stuff going on because we're using sound from the position sensor to measure the distance to the water, and we're also recording the sound level, but you can see pretty clearly here just before 19 centimeters is where the resonance is. You can see a pretty strong peak in the intensity there. This kind of noisy bit over here, I think, is from the sonar, so we'll not worry about that too much for now. Okay, so now that you've seen the resonance, I'm going to get all this stuff out of the way and just record the data for the experiment. The technique with the microphone doesn't work as well further down into the tube because the sonar sound gets even more in the way. But I thought it'd be cool to at least see the first resonance that way. The human ear is a very sensitive detector of sound, and so this experiment actually works really well, just using your ear to detect the sound level and listening for the resonance and adjusting the water level until you find it. So I'm going to go ahead and do that, and I'll report the results. Is at 512 hertz from the function generator. I found a resonance at 15.9 centimeters and 49.8 centimeters on the ruler, and that was with a room temperature of 23.5 C. So with these two distances, we can figure out the wavelength of the sound, and we know the frequency and the wavelength, so putting those together, we can figure out the speed of sound. You can use that to compensate for the temperature dependence for calculating a reference. Also, I figured I would just try using the microphone on my phone here. I'm going to put it right up to the top of the tube and see if you can hear the resonance when I move the water level through it. So here comes the water, and I'll go to that first one at 15.9. I'm just going to hold the phone with the microphone next to the tube so you can listen. I'm at 10, and I'm just going to slide it down, and you'll hear it go through the resonance, hopefully. So the water level is down at 18, 19 now. I'll slide it back up through resonance one more time. And yeah, if you heard that get loud in the middle there, that was passing through the resonance.